Good day, everyone, and welcome to Chapter 14 of our ASNT Level III Non-Destructive Testing Certification Program. In this chapter, we're going to study one of the most specialized and fascinating radiographic inspection methods used in the NDT industry, Neutron Radiographic Testing, commonly referred to as NR. Now, many inspectors are already familiar with conventional radiography using X-rays or gamma rays. However, neutron radiography operates on an entirely different physical principle. Although both methods produce radiographic images, the way neutrons interact with matter is fundamentally different from the way X-rays and gamma rays interact with materials. This unique behavior allows neutron radiography to reveal discontinuities and internal features that conventional radiography simply cannot detect. Throughout this chapter, we'll learn where neutrons come from, how they're produced, how they're slowed down and shaped into a usable inspection beam, how they interact with different materials, and finally, how those interactions are converted into high-quality radiographic images. We'll also examine practical industrial applications in aerospace, nuclear power, defense, turbine manufacturing, and advanced composite inspection, where neutron radiography provides capabilities unmatched by any other NDT method. As always, this course is designed not only to help you succeed in your ASNT Level III certification examination, but also to prepare you to understand the engineering principles behind the inspection process. As we progress, I'll highlight common examination topics, practical field considerations, and misconceptions that often lead to incorrect answers during certification exams. So, with that introduction complete, let's begin by understanding exactly what you'll be expected to master by the end of this chapter.
Before we begin discussing neutron sources and imaging principles, let's establish the learning objectives for this chapter. Having a clear understanding of these objectives will help you focus on the concepts that are most important for both industrial practice and your Level III certification examination. Our first objective is to understand what neutron radiographic testing actually is. You'll learn how neutron attenuation differs fundamentally from X-ray and gamma ray attenuation, and why these two radiographic methods often produce completely different images of the same component. Next, we'll answer an important question. Why is neutron radiography so valuable? One of its greatest advantages is its ability to reveal hydrogen-rich materials, such as water, rubber, plastics, adhesives, lubricants, and fuel, even when they're enclosed within dense metallic components. This capability makes neutron radiography unique among non-destructive testing methods. We'll then explore the industries where neutron radiography is commonly applied. These include aerospace inspections, pyrotechnic and ordnance components, nuclear fuel examination, composite structures, turbine blades, and other critical applications where conventional radiography has limitations. Another major objective is exam preparation. Throughout this chapter, we'll study the three neutron sources, the purpose of moderators and collimators, and the differences between neutron absorption and neutron scattering. These topics are among the most frequently tested concepts in ASNT Level III examinations. Finally, we'll discuss the industrial role of neutron radiography. It's important to understand that NR is not a replacement for conventional radiography. Instead, it complements X-ray and gamma ray inspection by providing information that photon-based radiography cannot reveal. By the end of this chapter, you should be able to explain not only how neutron radiography works, but also when it should be selected as the preferred inspection method and why it offers unique advantages in certain applications. Now that we've established our learning goals, let's begin by introducing neutron radiography itself and comparing it with the radiographic techniques you've already studied. Now let's begin by comparing neutron radiography with the conventional radiographic methods you're already familiar with. In the previous chapter, we studied X-ray and gamma-ray radiography. Both of those methods use photons, and their ability to penetrate a material depends primarily on the material's electron density. In simple terms, dense metals such as steel, lead, and tungsten strongly absorb X-rays and gamma rays, while lighter materials allow more radiation to pass through. Neutron radiography works on an entirely different principle. Instead of interacting with the electron cloud surrounding an atom, neutrons interact directly with the atomic nucleus. This single difference completely changes the appearance of the radiographic image. This is one of the most important concepts in this chapter. So let's take a moment to understand it clearly. With conventional radiography, dense metallic components dominate the image because they absorb most of the radiation. As a result, materials such as rubber seals, plastic inserts, adhesives, water, lubricants, or fuel inside a metal assembly may be difficult, or even impossible, to detect. Neutron radiography reverses this behavior. Many dense metals, including steel, titanium, and lead, are relatively transparent to thermal neutrons. On the other hand, materials containing hydrogen absorb and scatter neutrons very effectively. As a result, substances such as water, rubber, plastics, adhesives, oils, and fuels appear with excellent contrast. This unique characteristic makes neutron radiography particularly valuable when inspecting components that contain both metallic structures and non-metallic internal materials. For example, imagine inspecting a sealed hydraulic actuator. An X-ray image may clearly show the metal housing, but reveal very little about the hydraulic fluid inside. A neutron radiograph, however, can clearly display the fluid level, rubber seals, plastic components, and other hydrogen-rich materials hidden within the same assembly. This is why neutron radiography is often described as the perfect complement to conventional radiography. Each method reveals information that the other cannot. Before we move forward, remember this comparison because it's one of the most frequently tested concepts in Level III certification examinations. X-ray and gamma radiography interact primarily with the electron cloud. Neutron radiography interacts primarily with the atomic nucleus. If you understand this fundamental difference, you'll find the rest of the chapter much easier to follow. Now that we've established the fundamental difference between conventional radiography and neutron radiography, let's discuss where neutron radiography truly excels and where its practical limitations exist. As Level 3 inspectors, selecting the correct NDT method is just as important as performing the inspection itself. Every inspection technique has strengths and weaknesses, and understanding those characteristics allows us to make sound engineering decisions. Let's begin with the advantages. One of the most remarkable features of neutron radiography is that its penetration is not significantly affected by many dense engineering metals. Materials such as lead, steel, iron, and titanium, which strongly absorb X-rays and gamma rays, allow thermal neutrons to pass with relatively little attenuation. This gives neutron radiography a unique capability when inspecting assemblies that combine metal structures with non-metallic internal components. Another major advantage is its exceptional sensitivity to hydrogen-containing materials. Water, oils, fuels, plastics, rubber, adhesives, sealants, and composite materials all interact strongly with neutrons. This makes neutron radiography invaluable for detecting moisture ingress, inspecting bonded structures, verifying fuel distribution, and examining sealed components where conventional radiography provides limited information. Neutron radiography also complements conventional radiography rather than replacing it. In many industries, both methods are used together because each reveals different information. A conventional radiograph may clearly display defects in a metal casting, while a neutron radiograph can reveal trapped moisture, missing adhesive, damaged seals, or internal polymer components hidden within the same assembly. This capability has made neutron radiography especially valuable in aerospace, defense, nuclear engineering, and advanced composite manufacturing. Now let's discuss the limitations. Perhaps the greatest limitation is the availability of neutron sources. Unlike X-ray machines or gamma-ray cameras, neutron-producing facilities are relatively rare and require substantial investment. This immediately limits the widespread use of neutron radiography. Another important consideration is neutron activation. During exposure, neutrons may be absorbed by the test object, causing certain materials to become temporarily radioactive. Although this activation can often be managed safely, it introduces additional handling procedures and radiological controls that are generally unnecessary in conventional radiography. Facility requirements are also much more demanding. Neutron radiography requires specialized shielding, licensing, radiation protection programs, and highly controlled operating environments. These facilities are expensive to build and maintain. Finally, portability is extremely limited. While conventional gamma-ray radiography can often be performed directly in refineries, pipelines, or construction sites, neutron radiography is almost always conducted at dedicated research reactors, accelerator facilities, or specialized inspection laboratories. As inspectors, it's important to understand that neutron radiography is selected not because it is universally superior, but because it provides unique information that other inspection methods simply cannot obtain. When choosing an NDT method, always consider the inspection objective first. The best method is the one that provides the information needed with the greatest reliability, safety, and efficiency. Now that we've discussed the strengths and limitations of neutron radiography, the next logical question is, where do neutrons actually come from? In the next section, we'll examine the three primary neutron sources used in industrial neutron radiography. Now we begin one of the most important sections of this chapter, and I want everyone to pay close attention because this topic appears repeatedly in ASNT Level III examinations. A common exam question is straightforward. What are the three sources of neutrons used in neutron radiography? The correct answer is radioisotopes, neutron accelerators, nuclear reactors. Let's understand each one conceptually before studying them in detail. The first source is the radioisotope. Certain radioactive materials naturally emit neutrons as they undergo nuclear decay. These sources are compact, reliable, and continuously produce neutrons without requiring an external power supply. Because they are always emitting radiation, however, they must be handled under strict radiation safety procedures. The second source is the neutron accelerator, also called a neutron generator. Instead of relying on radioactive decay, an accelerator produces neutrons by accelerating hydrogen isotopes at very high speeds and causing them to undergo nuclear fusion. One significant advantage of this system is that it can be switched on when needed and switched off after the inspection is complete. The third source is the nuclear reactor. Reactors generate neutrons through a controlled chain fission reaction involving uranium-235 fuel. Because millions of fission reactions occur every second, nuclear reactors provide an extremely intense neutron flux, making them ideal for high-quality neutron radiography and scientific research. Each source has its own advantages, operating principles, and practical applications. Smaller facilities may use radioisotope sources, while major research laboratories often rely on accelerators or nuclear reactors to produce the neutron beam. For your examination, remember that collimators and moderators are not neutron sources. They are beam conditioning devices used after the neutrons have already been generated. This distinction frequently appears in multiple-choice questions. In the next 3 slides, we'll study each neutron source individually, beginning with radioisotope neutron sources. Now let's examine the first method used to generate neutrons for neutron radiography. Radioisotope neutron sources. This is one of the oldest methods of producing neutrons and remains an important topic in Level III certification examinations. Before discussing the individual isotopes, let's understand the basic principle. A radioisotope is an unstable atomic nucleus because the balance between protons and neutrons inside the nucleus is unstable. The atom naturally seeks a more stable state by emitting radiation. Certain radioisotopes release neutrons directly through spontaneous fission, while others generate neutrons through nuclear reactions involving alpha particles and light elements, such as beryllium. Let's look at the 2 most important sources you'll encounter. The first is californium-252, commonly written as CF-252. This is the preferred radioisotope for neutron radiography because it undergoes spontaneous fission and produces a relatively high neutron output without requiring an external power source. Its neutron energy is moderate, making it well-suited for industrial neutron imaging. In addition, its compact physical size allows it to be incorporated into specialized neutron radiography systems where space is limited. However, don't assume that portable means inexpensive or easy to obtain. Californium-252 is extremely costly to produce, requires strict regulatory control, and has a relatively short half-life of about 2.6 years. Over time, its neutron output decreases, eventually requiring source replacement. The second important source is americium-241 combined with beryllium, commonly referred to as AM-241/Be. Unlike californium-252, this source does not produce neutrons through spontaneous fission. Instead, americium emits alpha particles that strike a beryllium target. This nuclear reaction releases neutrons with higher energy than those produced by CF-252. One major advantage of AM-241/Be is its exceptionally long half-life, approximately 432 years. That means the source remains usable for decades. However, because of its higher neutron energy, it is not always the preferred choice for high-resolution neutron radiography. From a practical standpoint, you'll rarely encounter these sources in routine field inspections. Most neutron radiography today is performed in dedicated laboratories because of the cost, licensing requirements, radiation protection measures, and specialized equipment involved. Now here's an important point for your Level III examination. The reason radioactive decay occurs is the same principle you studied in conventional gamma radiography. An unstable nucleus seeks stability by emitting radiation. The difference is simply the type of radiation being emitted. So remember, CF-252 produces neutrons through spontaneous fission. AM-241/Be produces neutrons through alpha bombardment of beryllium. Understanding that distinction will help you answer several common certification questions. Now let's move to the second neutron source, where neutrons are generated not by radioactive decay, but through controlled nuclear fusion. Our second neutron source is the neutron accelerator, sometimes called a neutron generator. Unlike radioisotope sources, neutron generators do not rely on radioactive decay. Instead, they produce neutrons only when the system is operating. This is one of their greatest advantages. Before understanding how the generator works, let's review the hydrogen isotopes involved in the process. Hydrogen exists in three naturally recognized forms. The first is protium, which consists of one proton and no neutrons. The second is deuterium, containing one proton and one neutron. The third is tritium, which contains one proton and two neutrons. In neutron generators, deuterium or tritium ions are accelerated to extremely high velocities using electrical fields. These high-speed particles then collide with a target containing hydrogen isotopes. When these nuclei collide under the proper conditions, they undergo nuclear fusion. Fusion releases a tremendous amount of energy. More importantly, for neutron radiography, it also releases a free neutron. There are two fusion reactions you should remember. The first is the deuterium-tritium reaction, commonly called the DT reaction. This reaction produces neutrons with an energy of approximately 14 mega-electron volts, making it the highest output reaction used in neutron generators. The second is the deuterium-deuterium reaction, or DD reaction. This produces neutrons with an energy of approximately 2.5 mega-electron volts. For examination purposes, remember that DT produces significantly higher neutron energy than DD. One of the biggest operational advantages of neutron generators is that they can be switched on and off. Unlike radioisotope sources, they do not continuously emit radiation when not in use. This greatly simplifies storage, transportation, and radiation safety procedures. However, this advantage comes with a trade-off. Neutron generators require sophisticated electrical systems, vacuum equipment, cooling systems, and high-voltage components. As a result, they are considerably more expensive to purchase and maintain than conventional radioisotope sources. In industrial applications, neutron generators are often selected when operators require precise control over neutron production without maintaining a continuously radioactive source. For your certification examination, remember these key points. Neutron generators use fusion, not radioactive decay. The two important reactions are DT and DD. DT produces approximately 14 mega-electron volts neutrons. DD produces approximately 2.5 mega-electron volt neutrons. Most importantly, neutron generators can be switched on and off. Now we've covered spontaneous decay and nuclear fusion. Our final neutron source uses an entirely different process, nuclear fission inside a reactor, which provides the highest neutron output available for neutron radiography. We've now reached the third and most powerful neutron source used in neutron radiography, the nuclear reactor. While radioisotopes generate neutrons through spontaneous decay and neutron generators rely on fusion, nuclear reactors produce neutrons through a controlled chain fission reaction. Let's walk through the process step by step. The fuel most commonly used in neutron radiography reactors is uranium-235, often written as U-235. When a free neutron strikes a U-235 nucleus, that nucleus absorbs the neutron and briefly becomes an unstable uranium-236 atom. This unstable nucleus cannot remain intact. Almost immediately, it splits into two smaller nuclei, called fission fragments. Common examples include krypton and barium, although many other combinations are possible. This splitting process releases an enormous amount of energy. More importantly, for neutron radiography, it also releases 3 additional neutrons. Each of these newly released neutrons can strike another uranium-235 nucleus, causing another fission event. Those reactions release even more neutrons. This repeating process is known as a chain reaction. Inside a properly controlled reactor, billions of these reactions occur every second, creating an extremely intense neutron flux. That high neutron intensity makes nuclear reactors ideal for high-resolution neutron radiography, advanced materials research, and scientific investigations. Now, let's address a common Level III examination mistake. Students often confuse the fission products, such as krypton and barium, with the moderator that we'll discuss in the next section. These are completely different concepts. Krypton and barium are simply the fragments produced when uranium splits. A moderator, on the other hand, is a material used later in the process to slow down fast neutrons so they become more effective for imaging. Keep those two ideas separate in your mind. Before we leave this slide, let's review all three neutron sources using a simple memory aid. Radioisotope produces neutrons through radioactive decay. Accelerator produces neutrons through fusion. Reactor produces neutrons through fission. A useful mnemonic is RAR. Radioisotope decays. Accelerator fuses. Reactor splits. If you remember those three words, you'll answer one of the most common neutron source questions correctly. Now that we've learned how neutrons are generated, the next question is equally important. The neutrons leaving these sources are fast, energetic, and traveling in every direction. They are not yet suitable for producing a high-quality radiographic image. So how do we transform this chaotic stream of neutrons into a controlled inspection beam? That's exactly what we'll explore in the next slide as we discuss beam preparation through moderation and collimation. Now that we've learned how neutrons are produced, let's look at what happens immediately after they leave the source. This is a critical step because the neutrons generated by a radioisotope, accelerator, or reactor are not immediately suitable for radiographic imaging. If we were to expose a test object directly to these fast, randomly scattered neutrons, the resulting image would have poor contrast, excessive blur, and very little diagnostic value. Before we can produce a useful radiograph, the neutron beam must be conditioned. This beam preparation consists of two essential stages: moderation and collimation. Let's begin with the moderator. When neutrons leave their source, they possess very high kinetic energy. These are known as fast neutrons. While fast neutrons are energetic, they are not ideal for high-quality neutron radiography because they interact less effectively with many of the materials we want to inspect. To improve image quality, we must slow these neutrons down. This is the job of the moderator. A moderator is typically a material rich in light nuclei, such as heavy water, which causes repeated collisions with the neutrons. With each collision, the neutron loses a small amount of kinetic energy until it eventually becomes a thermal neutron. Thermal neutrons travel much more slowly and produce significantly better image contrast because their interaction with atomic nuclei is more predictable and efficient. Think of it this way. Imagine trying to take a sharp photograph from a speeding vehicle. The image will be blurred. But if the vehicle slows down, the picture becomes much clearer. In much the same way, slowing neutrons improves the quality of the radiographic image. Now let's move to the second stage, the collimator. Even after moderation, neutrons are still traveling in many different directions. If they continue to spread out, the image will become distorted and lose definition. The purpose of the collimator is to shape these scattered neutrons into a well-defined, nearly parallel beam directed toward the test object. This is similar to the reflector inside a flashlight. Without the reflector, light spreads everywhere. With the reflector, the light is focused into a controlled beam. A neutron collimator performs the same function. There are two common collimator designs. The first is the multi-tube collimator, which produces a highly parallel neutron beam suitable for precision imaging. The second is the divergent collimator, which uses a cone-shaped geometry to direct neutrons toward larger inspection areas. Both designs are lined with highly neutron-absorbing materials such as boron, cadmium, or gadolinium. These materials absorb stray neutrons before they reach the detector, preventing image blur and improving contrast. This is another concept that frequently appears in Level 3 examinations. Remember, the moderator slows the neutrons. The collimator shapes the beam. They perform completely different functions, and confusing the two is a common exam mistake. Now that we've prepared the neutron beam, the next step is to understand what happens when those neutrons actually enter the test specimen. Let's examine how neutrons interact with matter.
We've successfully generated the neutron beam and prepared it for inspection. Now comes the most important part of the imaging process. What actually happens when neutrons enter the test object? Unlike X-rays, which interact mainly with electrons, neutrons travel through the material until they encounter an atomic nucleus. When this interaction occurs, two primary outcomes are possible. The neutron may be absorbed or it may be scattered. Let's examine each mechanism separately. The first mechanism is absorption. During absorption, a thermal neutron is captured by the atomic nucleus. Instead of passing through the material, the neutron becomes part of that nucleus, increasing its atomic mass by 1. This often creates a new isotope, and in many cases, that isotope is radioactive. For example, cobalt-59 can absorb a neutron and become cobalt-60, a well-known radioactive isotope that later emits beta particles and gamma radiation. This phenomenon is known as neutron activation. Earlier in the chapter, we mentioned that neutron radiography can activate certain materials. Now you understand why. This process also forms the basis of several neutron imaging and analytical techniques used in nuclear engineering. Now let's discuss the second mechanism, scattering. Scattering occurs when the neutron strikes a nucleus but is not captured. Instead, it changes direction and often loses energy. There are two forms of scattering. The first is elastic scattering. Here, the neutron behaves much like a billiard ball striking another ball. Energy is transferred during the collision, but the nucleus remains in its original energy state. Hydrogen is particularly effective at slowing neutrons through elastic scattering because its nucleus has nearly the same mass as the neutron. This is one reason why hydrogen-rich materials interact so strongly with thermal neutrons. The second type is inelastic scattering. In this case, the neutron transfers part of its energy to the nucleus, exciting it to a higher energy level. When the nucleus returns to its normal state, it emits gamma radiation. These unwanted gamma rays create background noise and reduce image quality. Therefore, inelastic scattering is generally undesirable in neutron radiography because it decreases image contrast. For examination purposes, remember these key concepts. Absorption captures the neutron. Elastic scattering changes the neutron's direction and slows it down. Inelastic scattering excites the nucleus and produces gamma radiation. Understanding these interactions explains why different materials appear differently in neutron radiographs. Now that we've seen how neutrons interact with the specimen, let's answer another important question. Neutrons are invisible. So how do we convert an invisible neutron beam into a visible image that inspectors can analyze? That's the subject of our next slide.
At this stage of the inspection, the neutrons have already passed through the test object. They now carry valuable information about the internal structure of the component. However, there is one major challenge. Neutrons cannot be seen by the human eye, and they do not directly expose conventional radiographic film in the same way that X-rays or gamma rays do. So how do we produce an image? The answer lies in conversion screens. A conversion screen transforms the energy carried by neutrons into another form of radiation or light, that can be detected by film, digital detectors, or imaging cameras. There are two primary categories of converter screens. The first is the metallic foil converter. When neutrons strike metallic foils, nuclear reactions occur that produce beta particles, conversion electrons, or gamma radiation. These secondary radiations expose the film and create the radiographic image. Among all metallic converter materials, one stands above the rest: gadolinium. Gadolinium has an exceptionally high neutron absorption cross-section, making it extremely efficient at converting neutron energy into detectable radiation. As a result, gadolinium provides the highest image contrast and the best spatial resolution. This is one of the most frequently repeated questions in ASNT Level III examinations. If you're asked, which metallic foil provides the best neutron radiographic image quality? The correct answer is gadolinium. The second category is the light-emitting screen, also known as a scintillation screen. These screens contain phosphor materials enriched with lithium or boron. When neutrons interact with these materials, alpha particles are produced. Those alpha particles excite the phosphor, causing it to emit visible light. That light is then captured by cameras or digital imaging systems, allowing real-time neutron imaging. Modern neutron radiography increasingly uses these digital systems because they provide immediate image acquisition, faster inspections, and easier data storage. As Level 3 inspectors, always remember that neutron radiography is a two-stage imaging process. First, neutrons pass through the specimen. Second, the converter screen transforms those invisible neutrons into a visible image. Without the conversion process, there would be nothing for the inspector to evaluate. Now that we understand how the image is created, the next step is learning how to interpret that image correctly and recognize the unique features that distinguish neutron radiographs from conventional X-ray images. Now that we've learned how neutron radiographic images are produced, let's focus on one of the most important skills you'll develop as an NDT professional image interpretation. Remember, producing a radiograph is only the first step. The real value of any inspection lies in the inspector's ability to correctly interpret what the image is telling us. On this slide, we have an excellent comparison that demonstrates the unique capability of neutron radiography. Both images show the same motorcycle, but each was produced using a different radiographic method. Let's start by looking at the neutron radiograph, shown on the left. Notice that several components which would normally be difficult to distinguish in conventional radiography are now clearly visible. The fuel inside the fuel tank can be identified, the rubber tires are clearly defined, and the plastic seat stands out with excellent contrast. These materials all have one thing in common: they contain a significant amount of hydrogen, and hydrogen interacts very strongly with thermal neutrons. Now compare that with the conventional X-ray radiograph on the right. Here, the metallic components dominate the image. The engine, frame, suspension, wheels, and other structural metal parts are displayed with excellent clarity because X-rays are strongly attenuated by dense materials. However, many of the non-metallic components that were obvious in the neutron image are much less visible or may not be distinguishable at all. This comparison perfectly illustrates the fundamental difference between the two methods. Neutron radiography highlights hydrogen-rich materials. Conventional radiography highlights dense metallic structures. Neither image is more correct than the other. Each provides different information about the same component. Now, let's think about this from an industrial perspective. Suppose you're inspecting an aerospace hydraulic actuator. If your objective is to verify the condition of the steel housing, conventional radiography may provide all the information you need. However, if you're trying to determine whether hydraulic fluid is present, whether an O-ring has been installed correctly, or whether moisture has entered the assembly, neutron radiography becomes the preferred inspection method. The same principle applies in nuclear engineering, turbine manufacturing, defense systems, and composite structures. Many critical components contain both metallic and non-metallic materials. By selecting the appropriate radiographic technique, or by using both methods together, you can obtain a much more complete understanding of the component's internal condition. Here's an important examination point. Many Level 3 candidates make the mistake of interpreting neutron radiographs using the same thought process they apply to X-ray images. Avoid that mistake. The image contrast in neutron radiography is governed by nuclear interactions, not electron density. Because of this, the appearance of materials can be completely different from what you expect in conventional radiography. Before we move to the next slide, I'd like you to remember one simple principle. A good technician can read a radiograph. An experienced Level 3 inspector understands why the image looks the way it does and knows which inspection method will provide the information needed. That ability to select and correctly interpret the appropriate NDT method is one of the defining responsibilities of a Level 3 professional. Now that we've learned how to interpret neutron radiographic images, let's move on to a direct comparison between neutron radiography and conventional radiography, where we'll summarize their differences, strengths, limitations, and typical industrial applications. Now that we've seen how neutron radiographs are interpreted, let's compare neutron radiography with conventional radiography, which includes both X-ray and gamma-ray radiography. This comparison is extremely important because, as an NDT professional, one of your responsibilities is selecting the most appropriate inspection method for a particular application. Understanding the strengths and limitations of each technique allows you to make technically sound and cost-effective inspection decisions. Let's begin with the basic principle. Conventional radiography uses photons, either X-rays produced electrically or gamma rays emitted from radioactive isotopes. These photons interact primarily with the electron cloud surrounding atoms. Because dense materials contain more electrons, they absorb more radiation. As a result, heavy metals such as steel, lead, and tungsten appear with high contrast, making conventional radiography an excellent method for inspecting welds, castings, pressure vessels, and structural components. Neutron radiography works differently. Instead of interacting with electrons, neutrons interact directly with the atomic nucleus. This difference completely changes the image characteristics. Materials that contain hydrogen, such as water, lubricants, adhesives, plastics, rubber, fuels, and sealants interact very strongly with neutrons and therefore appear clearly in the radiographic image, even when enclosed within dense metal assemblies. Let's use a practical example. Imagine you're inspecting an aircraft hydraulic actuator. If your objective is to detect cracks in the steel housing, conventional radiography is likely the better choice because it provides excellent definition of metallic structures. However, if your objective is to verify the presence of hydraulic fluid, inspect internal O-rings, confirm adhesive bonding, or detect trapped moisture, neutron radiography becomes the superior method because these hydrogen-rich materials are clearly visible. This is why we often say that the inspection objective determines the inspection method. Now let's compare a few other characteristics. Conventional radiography has the advantage of portability. X-ray machines and gamma-ray projectors can be transported to fabrication shops, refineries, pipelines, and construction sites, making field inspections practical and efficient. Neutron radiography, on the other hand, usually requires specialized facilities equipped with neutron sources such as nuclear reactors, neutron generators, or Californium-252 systems. These facilities involve higher installation costs, specialized shielding, radiation safety programs, and trained personnel. Another important difference is activation. X-rays and gamma rays generally do not make the inspected component radioactive. With neutron radiography, however, some materials may absorb neutrons and become temporarily activated. For that reason, inspectors must evaluate activation potential before planning the inspection and follow appropriate handling and decay procedures afterward. Now, here's an important point for your Level 3 examination. Students are often asked, which method is better? The correct answer is neither. That question itself is misleading. Each method provides different information because each interacts with matter in a different way. In many aerospace, nuclear, and defense applications, both neutron radiography and conventional radiography are performed on the same component. The two images are then evaluated together, giving inspectors a much more complete understanding of the internal condition of the part. Before we move on, I'd like you to remember one simple comparison that summarizes this entire slide. Conventional radiography is best for examining metallic structures. Neutron radiography is best for revealing hydrogen-rich materials hidden inside those structures. Neither replaces the other. Instead, they work together to provide a complete picture of the component being inspected. With that comparison complete, we've now covered the fundamental principles: equipment, neutron sources, image formation, interpretation, and industrial applications of neutron radiography. Let's move into the final section of this chapter, where we'll review the key concepts and prepare for certification-style questions. Now that we've covered each individual component of neutron radiography, let's bring everything together by reviewing the complete inspection process from beginning to end. As a Level 3 professional, you should be able to explain this sequence confidently because it demonstrates your understanding of how every stage contributes to producing a high-quality radiographic image. The process begins with the neutron source. Depending on the facility, this may be a radioisotope such as californium-252, a neutron generator based on deuterium-tritium fusion, or a nuclear reactor producing neutrons through controlled fission. Regardless of the source, the objective is the same: to generate a stable neutron beam for inspection. The next stage is moderation. The neutrons produced by the source are initially fast neutrons with very high energy. These are passed through a moderator, commonly heavy water or another hydrogen-rich material, where repeated collisions reduce their energy. The result is a beam of thermal neutrons, which provides much better interaction with the specimen and produces superior image quality. After moderation, the beam enters the collimator. Remember, the moderator slows the neutrons, but the collimator shapes them. The collimator removes stray neutrons and directs the beam into a controlled, nearly parallel path. This improves image sharpness and minimizes scattered radiation that could reduce contrast. The conditioned neutron beam now passes through the test object. As the neutrons travel through the component, they interact with the atomic nuclei of different materials. Some neutrons are absorbed, others are scattered, and the remaining neutrons continue toward the detector. These interactions create the attenuation pattern that contains all of the inspection information. The transmitted neutrons then reach the converter screen. Since neutrons cannot directly expose conventional film, the converter transforms neutron energy into secondary radiation or visible light. Materials such as gadolinium are commonly used because they efficiently convert neutron interactions into detectable signals while maintaining excellent image resolution. Finally, the image is captured using radiographic film or a modern digital detector. The inspector evaluates the resulting radiograph for missing adhesive, trapped moisture, damaged seals, fuel distribution, corrosion, or other internal features that are difficult or impossible to detect using conventional radiography. Before every inspection, experienced inspectors also verify beam alignment, exposure parameters, image quality indicators, and detector performance to ensure the radiograph meets the required acceptance standards. If you're ever asked to explain neutron radiography during an interview or examination, remember this simple sequence: neutron source, moderator, collimator, test object, converter, screen image interpretation. If you understand what happens at each stage, you'll understand the entire neutron radiography process. Now let's move into a section that's especially valuable for anyone preparing for technical interviews or ASNT Level III certification. Interviewers are rarely interested in memorized definitions. Instead, they want to know whether you can apply engineering principles to real inspection situations. Let's consider some typical interview questions. The first question is, why would you recommend neutron radiography for a particular inspection? A strong answer begins by identifying the inspection objective. If the component contains hydrogen-rich materials such as water, hydraulic fluid, lubricants, adhesives, rubber seals, plastics, or composite cores enclosed within metal, neutron radiography provides information that conventional radiography may not reveal. Always explain your reasoning rather than simply naming the inspection method. Another common question is, What are the limitations of neutron radiography? A complete answer should mention that neutron sources are expensive and generally available only in specialized facilities. The equipment requires extensive shielding, strict radiation protection procedures, and qualified personnel. In addition, neutron activation may occur, meaning some materials become temporarily radioactive after inspection and require controlled handling. You may also be asked, can neutron radiography replace X-ray or gamma radiography? The correct answer is no. The two methods are complementary. Conventional radiography is excellent for examining metallic structures, while neutron radiography is ideal for revealing hydrogen-rich materials hidden inside those structures. Here's another question frequently asked in interviews. Why is gadolinium preferred as a converter material? Because gadolinium has one of the highest neutron absorption cross-sections of any practical material, this allows it to efficiently convert neutron interactions into detectable radiation, producing images with excellent contrast and high spatial resolution. When answering technical questions, follow a simple structure. First, explain the scientific principle. Second, relate it to the inspection process. Finally, describe its practical industrial application. This approach demonstrates not only technical knowledge, but also engineering judgment, which is exactly what employers expect from a Level III professional.
We've now reached the review section of this chapter. These questions are designed to reinforce the concepts we've studied and prepare you for certification examinations. I encourage you to pause after each question, think about your answer, and then compare it with the explanation. Question 1. Which radioisotope is commonly used as a neutron source for neutron radiography? The correct answer is californium-252, which produces neutrons through spontaneous fission and is widely used in neutron radiographic applications. Question 2. Which nuclear reaction produces neutrons in a neutron generator? The answer is nuclear fusion, specifically the deuterium-tritium or deuterium-deuterium reactions. Question 3. What is the purpose of the moderator? The moderator slows fast neutrons, converting them into thermal neutrons that are much more suitable for producing high-quality radiographic images. Do not confuse the moderator with the collimator. The collimator shapes the beam. The moderator slows the neutrons. Question 4. Which material is widely used as a neutron converter because of its excellent neutron absorption characteristics? The answer is gadolinium. Its high neutron absorption cross-section allows it to produce images with outstanding contrast and resolution. Question 5. Why is neutron radiography considered complementary to conventional radiography? Because each technique provides different information. Conventional radiography emphasizes metallic structures, while neutron radiography highlights hydrogen-rich materials such as water, rubber, plastics, adhesives, lubricants, and fuel. If you can confidently answer these questions and explain the reasoning behind each one, you've developed a strong understanding of the fundamental principles covered in this chapter. Congratulations! You have successfully completed Chapter 14, Neutron Radiographic Testing. Throughout this chapter, we've explored one of the most specialized non-destructive testing methods used in modern industry. We began by understanding the fundamental difference between neutron radiography and conventional radiography, learning that neutrons interact with atomic nuclei, while X-rays and gamma rays interact primarily with electrons. We then examined the three principal neutron sources: radioisotopes, neutron generators, and nuclear reactors, and discussed how moderators and collimators prepare the neutron beam for imaging. Next, we explored neutron interactions with matter, including absorption and scattering. and learned how converter screens transform invisible neutron energy into images that inspectors can evaluate. Finally, we studied practical industrial applications, image interpretation, and the situations where neutron radiography offers significant advantages over conventional radiographic methods. As you continue your preparation for the ASNT Level III examination, remember that success comes from understanding concepts rather than memorizing isolated facts. When you understand the physics behind the inspection process, you'll be able to analyze unfamiliar situations, solve technical problems, and confidently justify your inspection decisions. In professional practice, your responsibility extends far beyond operating equipment. A Level 3 inspector must select the appropriate inspection method, ensure compliance with applicable codes and standards, interpret results accurately, and provide technically sound recommendations that contribute to the safety and reliability of critical equipment. Thank you for your attention, participation, and commitment throughout this chapter. I hope this session has strengthened your understanding of neutron radiographic testing and increased your confidence in applying this specialized inspection method. I look forward to seeing you in the next chapter as we continue advancing your knowledge and skills in non-destructive testing. Thank you, and I wish you every success in your ASNT Level III certification journey.